All right, we are almost at the end of new content. We have new content today, and then only one more lecture after that. So if you look on the syllabus, it says that next week on Monday, we're going to have the last lecture, and then we're going to review on Wednesday. But I was thinking about that, and I was thinking it makes more sense to review on Monday so we can review some of the topics that will be on next week's Tuesday and Thursday exams. That way our review will benefit everyone rather than waiting till Wednesday where the review would really only benefit the students who have exams on Thursday. So we're going to switch that up. I think that makes the most sense. And next week, instead of having day 27 new content on Monday, we're going to have that on Wednesday of next week. And then on Monday of next week, we'll review, and we'll probably primarily review the topics that will be on next week's exams, which are day 12, exam 12. And then we'll cover the last bit of chapter 23, the day 27 lecture next Wednesday. And that will prepare you for exam 13, which will cover what we talked about today and next Wednesday. And you'll have that exam the following week. So hopefully that all makes sense. I did update those details on the syllabus. So you can check the syllabus out anytime and get that confirmation. All right, so our last chapter of the semester is chapter 23. The textbook has a few more chapters, but most of that is extra stuff that you wouldn't normally see covered in an OChem, sophomore level OChem sequence. But there's so much material already packed into the semester. We're not going to take the time to get into any of those additional chapters. So 23 is going to be the last chapter we cover, and it is about amines, which we have talked about a fair amount already, both in OChem 1 and OChem 2. So a lot of this will actually be reviewed, but there are some amine-specific details that we are going to talk about and get into in this chapter. So hopefully that will not be too much challenge material right at the end of the semester for y'all. So we talked about amines previously. We said amines are derivatives of ammonia. So technically ammonia is not an amine because it's not an organic compound. There's no carbon involved. But if we replace any one of these protons with any type of carbon group, you could put up to 3 carbon groups on the nitrogen. You need the lone pair, though, for it to be an amine. If you bonded the nitrogen with 3 or 4 carbon groups, or even 3 carbon groups and 1 proton, so if you had 4 total bonds on the nitrogen, it would take on a positive charge. That wouldn't be an amine. An amine requires the nitrogen to have a lone pair and only 3 bonds specifically. So this would be called an ammonium salt. It would have to come with a counterion like a chloride or something like that. So amines can be converted into ammonium salts in the presence of an acid if their lone pair picks up a proton. We'll talk about that. We'll talk about that a little bit more. So if we are specifically talking about amines, though, they come in 3 types: primary, secondary, or tertiary. And again, normally we think of primary, secondary, or tertiary as referring to the carbon that holds some group, right? So if this was an alcohol or a halide, this would be secondary alcohol or halide because it's on a secondary carbon. The carbon has 2 other carbons and it's presumed to have a hydrogen. But since most groups can only have 1 bond, we categorize the carbon that they're attached to. And we said that was useful because it helps us to recognize how much sterics there is and whether or not it can leave and create a stable carbocation, or if there's space enough for a nucleophile to come in and replace it. Talked about that in a lot of detail previously. Amines are categorized, though, based on how many carbons are directly attached to the nitrogen. So we've talked about this. A primary amine has 1 carbon group and 2 protons. Secondary amine has 2 carbon groups and 1 proton. Tertiary amine has 3 carbon groups. There's also something, this would be called a quaternary ammonium salt. So that would be if I had 4 R groups. Quat, obviously, it's prefixed for 4, so 4 R groups would be a quaternary ammonium salt. So that's technically, again, as we said, not an amine. But that would be what you would call it if you had 4 R groups instead of 3. And so we'll talk about how these differences in the number of R groups affect the properties and reactivity of amines. You should also be aware that amines are very common. There's lots of different amines that occur in natural products, and there's just a few examples of some compounds that are the active ingredients in certain drugs and medicines and biologically relevant molecules. So a lot of these are neurotransmitters or regulatory compounds that organisms have evolved to use to regulate their different chemical processes and signals that occur in organisms. And so a lot of those have hopefully relatable structures to you. I'm not going to get into a detail on that. You don't have to memorize those structures or anything, obviously. So we're going to talk about the amine functional group. As we said, the amine functional group has to have a lone pair on the nitrogen, and the nitrogen has to be bound to either carbons or hydrogen. Either way, whether it's carbon or whether it's a hydrogen here, the nitrogen is going to be more electronegative than either of those atoms, so the electrons it shares are going to be attracted more toward it than the other atoms. And that's why we see a fair amount of partial negative there, and then there's going to be a lot of partial positive around the outside. So if this were a flat structure, it'd be nonpolar, but we want to also keep in mind that it has a trigonal pyramidal shape. So normally we would draw that with the nitrogen at the top of the pyramid, and then whatever hydrogen or carbon group is attached would be at the bottom of the pyramid. And then as the electron density gets pulled to the top, you get a partial negative at the top and an average position of partial positive at the middle of the base of that pyramid at the bottom. So it does have a dipole. That makes it polar. It makes it readily soluble in a variety of polar solvents, depending on the size of the R group. Obviously, we know if I have a big nonpolar R group, or especially multiple big nonpolar R groups, it's going to decrease the solubility of this in polar solvents because the dipole will be a minor component of that structure compared to the size of the low polarity R groups. In terms of chemical reactivity, the simplest reaction that we can probably imagine an amine undergoing is a proton transfer. We know that the lone pair of the nitrogen is kind of in this sweet spot where the nitrogen's electronegative enough to attract electrons and create a significant partial negative on that lone pair, but it's not super electronegative, because if it were extremely electronegative, then it would hold on and attract its electrons too strongly to allow this lone pair to be effectively shared. So it's in this sweet spot where it's electronegative enough to have a large partial negative, but not too electronegative to allow that lone pair to be shared with another atom. So what we see with amines is that they can act as a base by sharing their lone pair with a proton. And this would be based by the Bronsted-Lowry definition. So it doesn't have to be a strong acid. Really, any acid, the nitrogen at least could potentially pick up a proton, become protonated, and then depending on the pKa of the acid versus the pKa of the conjugate of the amine, that would tell us how much this equilibrium favors the reactants versus the products. All right, so just to point that out here, HCl has a pKa of about -7. Most ammonium salts, their pKa's range from 0 in some rare examples to around 10 or so, and a standard one that just has regular alkyl groups nothing unusual going on, and maybe a hydrogen or two, usually the pKa of that's going to be around 10. So we know the equilibrium is going to favor the side with the larger pKa. And if it's -7 versus 10, that's 17 pKa units different. So we know this reaction is going to be 10 to the 17th more products than reactants. And so that's extremely product favored, right? So amines are pretty good bases, especially in the presence of a strong acid with a very low pKa. Those equilibria are going to shift toward the product side. Amines can also function as a nucleophile, which is the same as saying it's a Lewis base. Right? So specifically, the standard or more traditional definition of a base is the Bronsted definition, which means that it means picking up a proton, but generally the Lewis base is more general. That includes those types of reactions, but also reactions where the amine shares this lone pair with something other than a proton. And so typically we see that being a carbon, as long as there's a leaving group. We've seen lots of examples where an amine can attack a carbonyl compound, push electrons up in this manner. That occurs especially well if the oxygen's already protonated, or if there's something else like a chloride pulling electrons, creating even more partial positive to help the partial negative of the nitrogen attack, right? So we've seen those types of reactions. And that's pretty much what we're going to see amines doing. Acting as a base, either a traditional Bronsted base or as a nucleophile, which is the same as a Lewis base. So before we get into a lot of detail on that, we want to talk a little bit about naming amines. And we want to look at a couple different naming systems for amines. So I might ask you to draw an amine based on its name, or give the name for one that I've drawn for you on an exam. So I'm going to be prepared to answer that question whichever way it's asked. And one way to name amines is to just use the word amine as the parent name. And this is typically done especially for primary amines, because then all you have to do is name the carbon group as a substituent and put that out in front of the parent name. So if there's an ethyl group, it'd be ethylamine, an isopropyl group, isopropylamine, a cyclohexyl group, cyclohexylamine. And that's typically how you'll see things done with relatively small, simple structures where there's only one R group. We'll come back to that in a second. And you'll often see the same system used if there are multiple R groups. So depending on the size of the R groups, if they're all relatively small and they can be easily named, you might just name them and list them alphabetically before the name amine, which would be the parent name. So this amine has a methyl, an ethyl, and a propyl, and so we just list those in front of the word amine. Here I've got 3 methyls, so I have to say trimethyl, a couple ethyl groups, diethyl. So if you have the name amine, that basically just implies that you have a nitrogen. And then you have to look to see what substituents are bonded to that nitrogen. And anything, the nitrogen has to have 3 bonds and a lone pair. So if the name only tells you that there are 2 groups, you can assume that the remaining group is a proton. And likewise over here, if we just say the name is amine, that just implies a nitrogen with a lone pair. And if there's only one substituent listed in front of that, it doesn't mean there's only one substituent attached. It just means the other substituents are going to be protons, and that's a primary amine. So that's a pretty straightforward naming system for amines, and works for a lot of molecules. But sometimes the substituent is very large and not easy to name as a substituent or a side group or whatever. Right? So if I were thinking about this compound, if I wanted to name it amine, and it is a primary amine, there's only one R group attached, but then I have to name this R group as a substituent, and that's going to be a lot more challenging. So instead of using that system, the second system would be to include the amine with the longest chain of carbons that you can find and make that your parent name. And so if I have a 7-carbon parent chain with an amine group attached to it, then I would call that hept for 7. Heptane, because there's no alkene or alkyne, right? It could be heptene amine or heptyne amine if there were an alkene or an alkyne, a double or triple bond somewhere in this parent. But since there isn't, I would just have heptane, and then I take the E off the end of the word heptane and replace it with the suffix amine. So in the other system we used, the word amine was the entire parent name, and every carbon had to be accounted for with the substituent name. The difference here is the parent name includes the carbon chain and a locant or a number that tells us which carbon on the parent chain the amine group is connected to. Right, so if I have a 7-carbon chain with an OH here, it'd be heptanol. Heptane, take off the E and add the OL suffix. Here the suffix is just amine. So heptane amine, and we need the 2. Obviously this would also be 2-heptanol because the OH group's on carbon 2 of the parent chain. So here we have the NH2 group on carbon 2 of the parent chain, so it's 2-heptane amine. So that would be the parent, but then I have to count for substituents. So there's this methyl group on 4 and a methyl group on 6, so it'll be 4,6-dimethyl. And then as always, if there's a chiral center, we need to determine whether it's RRS or if there's an alkene. Depending on the structure of the alkene, it might need an E or Z configuration. Right, so we always want to look for stereochemistry and make sure we account for the stereochemistry in the name as well. We've done a lot of that, so I'll leave that up to y'all unless you have questions about it. So, if you want to analyze these and make sure they're both R configurations, and if you're not seeing that, let me know. We can discuss that some other time. Sometimes the amine group is easier named if it's not part of the parent. So that's the third method, right? So there's really 3 different important points here you want to keep in mind about naming amines. So if you have a nitrogen, an amine group, it's got a lone pair, you can name it as a substituent if it's inconvenient to include it as the parent chain. So right now I've got 1, 2, 3, 4 carbons here, so I know my parent name is going to be bute. And there's no alkenes or alkynes, so it's butane, not butene or butyne. So if I give the alcohol group a priority and put that on carbon 1 and include that as my parent chain, then I have butanol. And then I just have to start numbering with carbon 1 there, 2, 3, 4, and then I have an amine group on 4, so I can call that a 4-amino. And so if it's a substituent, it's not like a methyl or ethyl where it gets a YL. It's more like a chloro or a bromo where it gets an O at the end of it to indicate that O indicates that it's a substituent. It would also be okay with me if you name this with the amine as part of the parent. Right, so if I have 4 carbons, butane, and I take the E off of that butane and replace it with amine, butane amine would just be this compound if this were a hydrogen instead of an OH. So I have an OH on carbon 4. So I can also call that 4-hydroxy butanamine or 4-amino butanol. Either of those would be okay there. Here, we would want to include the carboxylic acid with the aromatic ring in our parent. Right, that's benzoic acid. So I've got the nitro group and the para position to the carboxylic acid. So I could call that para-nitro, or I could call it the amine group, para-amino or 4-amino benzoic acid. That's easier than trying to make this my parent name and call it aniline. And if I have an NH2 on a ring, that's aniline, but then I'd have to name this as a substituent, and that's a little trickier. So para-amino or 4-amino benzoic acid would probably be the easiest way to name that one. If you do have an NH2 group directly connected to an aromatic benzene ring, that is aniline. And then if there are other substituents on the ring, you can locate and name those as substituents. And that's another way to name amines if the nitrogen of the amine is directly connected to a benzene ring. If I've got multiple substituents, then I would number them. So here, if I use the name aniline, that implies that the nitrogen has to be bonded to carbon 1 of the aromatic ring. So this has to be carbon 1 if I use aniline as my parent name, which I should here. And then as I number around, I want to go in the direction where the first substituent I run into has the lowest number possible. So if I number around the ring clockwise, I don't get to the first substituent until carbon 3. If I number counterclockwise, I get the first substituent on carbon 2. So that is the correct way to number around that ring, and that's why I have a 2-fluoro, 5-ethyl, which are listed alphabetically. Talked about this one. So then the last major point about naming amines is sometimes you might have multiple substituents on the nitrogen. And we need a locant for that, or a way in the name to communicate where those groups are. Right? So if my parent chain here is the hexane, and I have an amine on carbon 3, if my structure looked like this, if this were my structure, I would have 1, 2, 3, 4, 5, 6. So my parent chain would be hex. There's no alkene or alkyne, so it's hexane. There's an amine on the parent chain, so I can include that in there. So hexane amine would be if those chloros weren't on there. But then I have 2 chloros on carbon 2, so 2,2-dichloro. So the numbers, once I make my parent name hexane, any number is going to tell me where on the hexane the groups are connected, right? That's why the 2,2 tells me that the chlorines are on carbon 2 of the hexane. And so if I have any other group, if I have a bromo on 1, I put 1 bromo. If I have a methyl on 5, I put 5 methyl. So any group that's on any of those 6 carbons from my hexane can be communicated, its location can be communicated by giving the number for which carbon of the hexane chain that group is connected to. But if I have a group connected to the nitrogen, it's not directly connected to the carbon chain. So we can't say this is 4-ethyl, but it's directly connected to the nitrogen. So instead of giving it a number, we just give it a letter. We say N-ethyl. That tells me that the ethyl group's connected to the nitrogen and not to one of the carbons in the parent chain. So then the full name here would still list things alphabetically. The chloro comes before the ethyl, which comes before the methyl. So I still have 2 chloros on carbon 2, an ethyl on the nitrogen, a methyl on the nitrogen, and then, I needed a 3 here, sorry about that. Because I still have to communicate where on the parent chain the amine is. If I don't, it would be assumed to be on carbon 1. So if the amine's not on carbon 1 of the parent chain, I need a locant for the amine as well. And then obviously as well, because there's a chiral center here on 3, that needs to be determined to be RRS. So, obviously when the molecule gets complicated, it gets a little trickier. So let's look at this one. So here I've got a structure with an amine. There's a couple different ways I could name this. So if the substituents are relatively simple, I could potentially try to name the molecule as amine as its parent name. And on this side, I've got an isopropyl. On this side, I've got a 2-methyl cyclohexyl group. That would have to be in parentheses. Well, actually, no, it wouldn't. Because there's no ambiguity about where the methyl group is on the structure. But then I'd still have to determine the configuration at these carbons in terms of whether they're R or S. And that gets a little tricky because, well, not really, I guess. Carbon 1 here, the prioritization, nitrogen will be the top priority, then this carbon, and then that carbon. So that'll be counterclockwise, and with the lowest priority group pointing out me, counterclockwise is actually R. Carbon 2, this group would be top priority, then this one, then the methyl would be 3, so going around clockwise in that situation, that would also be R. So then I would alphabetize this so the isopropyl come before the methyl. So it would be isopropyl 2-methyl cyclohexyl amine. That would be one way to name that. It's probably not the name I would expect you to come up with. So the other way to look at that would be to include the nitrogen and the longest chain of carbons as my parent name. So if this is my parent name, that would be cyclohexane. It's not a substituent in this case, so that's the main difference. Right? If I just write amine, then I have to name everything with a YL suffix because everything attached to the nitrogen is a substituent. But if I call it cyclohexane and get rid of this E and don't put the YL suffix here, without the YL suffix, I'm implying that the cyclohexane and the amine are my parent chain. And since the amine is on carbon 1, I don't need a locant for that. But then on carbon 2, I have a methyl. And then on the nitrogen, I have an isopropyl. So that would be N-isopropyl 2-methyl cyclohexane amine. And I would still need the stereochemical information there in the name as well. So here was the quiz question about naming. In this situation, there's really a couple names you could look, ways you could look at this as well, each of which I would accept as correct. So the first system we talked about would be where you use the nitrogen itself as the parent and just say amine. Now you've got three things: a methyl, a cyclopentyl, and this. So you'd have to name those and list them alphabetically. Methyl, cyclopentyl, and then this would be a phenyl. Right? So if it's not part of the parent chain, if it's a substituent, which is what it would be if I just have amine as the only part of my parent name, this would be a phenyl, and there'd be a chloro on 4 of that phenyl. So it'd be 4-chlorophenyl. And then I'd have to list those alphabetically. CH before CY, before M. So before chlorophenyl cyclopentyl, aromatic base, methyl amine. So that'll be one name for that compound. And when you see the name, you can draw the structure, because when you see amine at the end of the name and everything else ends in a YL, it tells you that the parent name is just the nitrogen and that these three groups are connected to the nitrogen: a 4-chlorophenyl group, a cyclopentyl group, and a methyl group. Alternatively, you could, it's going to get messy if I don't get rid of that. Alternatively, you could include the nitrogen and the ring as your parent name, because when you have a nitrogen on an aromatic ring, this is aniline. So my parent could be aniline, which would include the nitrogen and the ring. And then aniline then implies that when I use the name aniline, it implies that carbon 1 of the ring must be the carbon that the nitrogen is connected to in that name. And so then as I number around, I get a chlorine on carbon 4. So I can call that para-chloro, because it's in the para position with respect to the amine, or 4-chloro. So I've got a 4-chloro on my aniline. And then I've got the methyl and the cyclopentyl. They're not on a carbon that's numbered in the parent chain. They're on the nitrogen. So they would get a nitrogen locant. There's a methyl on the nitrogen, and there's a cyclopentyl on the nitrogen. So those again would be listed alphabetically. And the N obviously doesn't count alphabetically. It's the name of the substituent that counts. So CH comes before CY, comes before M, so I'd have 4-chloro, N, cyclopentyl, N, methyl amine, aniline. So that would be the other way to name that one. All right, so let's take a look at, now that we've learned the basics of naming amines, let's take a look at their properties and reactivities. So generally, the nitrogen atom of an amine is going to be sp3 hybridized, which means it's going to be trigonal pyramidal. Right, the lone pair is repelling the bonds, forcing them down away from it into the shape of a pyramid. The bond angles are going to be real close to 109.5. Why are the angles between the R groups a little smaller? And they won't always be the exact same angle just as well, right? So we want to recognize that a lone pair is an area of negative, and it's going to repel the bonded pairs a little bit more than the bonded pairs repel one another, because the lone pair doesn't have any protons around it shared with the nitrogen to balance out that negative. So it's got more concentrated negative than a bonded pair has due to the carbon and other hydrogens and positives that are kind of balancing out the negative of that electron cloud. So the lone pairs are always going to repel bonded pairs a little bit more, and that forces the bonded pairs to angle that's just smaller than 109.5, which is what it would be if all four groups of electrons spread out evenly. So we can say the lone pair repels the bonded pairs more than they repel one another. We can also look at the carbon-nitrogen bond, which is a little bit shorter than a carbon-carbon bond. And that's not surprising because a nitrogen's sp3 orbital is going to be a little bit more compacted than a carbon's sp3 orbital. So this is a little bit dramatic here, a little bit exaggerated, but to make the point, the nitrogen has more protons in its nucleus than carbon. So all of its orbitals are pulled a little closer to its nucleus than the orbitals would be for an atom that doesn't have as much positive. So for the nitrogen and carbon to bond, for carbon and carbon to bond, their elongated sp3 orbitals have to overlap head-on to make a sigma bond. For the nitrogen carbon, the atoms are going to be a little closer because the nitrogen's orbital is more compact. The carbon has to get closer to do effective head-on orbital overlap to make that sigma bond. Sometimes the nitrogen will be sp2 hybridized. Under what circumstances will that be the case? Well, that will be the case where the lone pair can experience resonance or conjugation. If it's conjugated with some other pi bond. Right, so just to point that out, if I have, I need a little more space. I got space here. Let's talk about that here. So let's say I've got aniline. Or maybe just an allylic amine group. It doesn't have to have any protons. Right? So in each one of these cases, there are p orbitals overlapping to form the pi bonds nearby. In the case of the ring, all the way around the ring. In the case of a standard alkene, just on the alkene. So the nitrogen could be sp3 and put the lone pair in a slightly more compact sp3 orbital, which stabilizes the electrons around this nucleus pretty well, but that still localizes the electrons around only one nucleus, and it doesn't allow for the molecular orbital to form with more orbital overlap that stabilizes the electrons even more. So putting the lone pair in a p orbital so that p orbital can overlap with the other p orbitals is going to be more favorable and stable for those electrons. So anytime the lone pair is conjugated, meaning it's in a p orbital adjacent to neighboring other p orbitals that already exist, the lone pair is going to be in a p orbital. That means the nitrogen is going to have to be sp2 hybridized to make 3 sigma bonds with its 3 sp2 orbitals overlapping head-on, and the lone pair will be in a p orbital so it can overlap with the other p orbitals and engage in resonance and conjugation that creates a more expanded molecular orbital that expands over more nuclei. It stabilizes the electrons more effectively. So you want to be aware of situations where the nitrogen's lone pair will be in a p orbital. When it comes to the stereochemistry of amines, it's not usually something we worry about. And the reason for that is because even if an amine is chiral, it can't usually be resolved from its enantiomer. And that means, for practical purposes, it's not going to be optically active. So if we look at the structure, it is chiral. It has 4 unique groups, one carbon group that's different from another carbon group that's different from another carbon group, and a lone pair. And if all 4 of those groups are unique, then when I draw its mirror image, they won't be superimposable, right? There's no way for me to flip this over like a pancake or rotate it in space and have everything line up on the other structure. If 2 structures are mirror images, but they're not superimposable, then they're enantiomers, and each one is chiral. However, with the lone pair, that creates a situation where the nitrogen can quickly actually shift back and forth between 2 different hybridizations. Right? So we already know that the nitrogen can adopt an sp2 hybridization, and it will pretty much permanently if its p orbital can overlap with neighboring p orbitals. But even when it can't, the sp3 hybridized lone pair in an sp3 orbital isn't really much more stable than the lone pair being in a p orbital. And we can measure the energy difference there. And at room temperature, there's enough energy in the collisions that occur to provide the energy for the rehybridization of the nitrogen into an sp2 hybridization. And we know from our experience now that every time a structure becomes flat, there's an equal chance if something were to attack it, it could come in from one side or the other. We're not attacking this nitrogen with anything. We just have to recognize that since this is the highest energy point on this energy diagram, the nitrogen is going to rehybridize into an sp3, and when it does, it's either going to put the electrons in a lone pair on one side, creating one enantiomer, or since when the p orbital forms, the electrons are equally distributed on both sides. When it rehybridizes into an sp3 hybridized nitrogen, the lone pair would maybe get onto the other side and form the sp3 orbital on the other side. So what this means is that these two enantiomers are rapidly interconverting. The molecule will temporarily and for a very minute moment in time rehybridize to sp2, and once it does, when it hybridizes back to sp3, it can go either direction. And so over time, you end up with a 50-50 mixture of these two, which means it's not going to be optically active. It's not going to rotate plane polarized light because one enantiomer would rotate the light one way and the other would cancel out with the opposite rotation. And we can't separate these enantiomers because they keep interconverting back and forth into one another. So then that really just means we don't have to worry about it. If I have a nitrogen that's chiral because it has three unique carbon or hydrogen groups and a lone pair, I don't have to worry about whether it's R or S, because if it is R, very soon half the molecules will be in the S format and shifting back and forth. So we don't really care too much about the chirality of amines because they flip back and forth like that. All right, so what about some of their physical properties? Well, we know that nitrogen is going to be capable of hydrogen bonding. So if I have a primary or secondary amine, then the big electronegativity difference here is going to create some very large partial charges, and another structure of the amine can do a nice hydrogen bond between its large partial negative on one structure and the large partial positive on a neighboring structure. The hydrogen bond here, though, is not as strong as the hydrogen bond that occurs when oxygen bonds with hydrogen. And the reason for that is because of the electronegativity difference, right? Nitrogen, hydrogen, the electronegativity difference is about, 3.0 to 2.1. It's about 1. The oxygen to hydrogen electronegativity difference is almost 1.5. So it's significantly larger difference here, which means we have significantly larger quantities of partial charge. It's a bit of an exaggeration, but the point is that the large partial negative, large partial positive in this hydrogen bond attracts the molecule significantly stronger than the hydrogen bond over here, which accounts for the large difference in their boiling points. Right? If when my structure is nonpolar and I can't hydrogen bond or form any dipole-dipoles, it will be a gas at very low temperatures because the attractions between this structure and a neighboring identical structure are very weak and very easily broken even at low temperatures. Once I have a dipole that can hydrogen bond, its boiling point is going to be much higher. But small amines are often still gases at room temperature because their hydrogen bonds aren't nearly as strong as those that involve oxygen because of the smaller quantities of partial charge that result from the smaller electronegativity difference. So those compounds boil a little more readily as well. So let's take a look at this trend here on the bottom of the slide. What we see here is 3 compounds that have the exact same formula. So these 3 are constitutional isomers. They each have the formula C3H9N. The difference is the connectivity. So either I have a primary amine, a secondary amine, or a tertiary amine, and we see significantly different boiling points. So since they have the same formula, which means they're all basically the same size, although this one is a little bit more compact because there's more branching, so this one's going to have a little bit less surface area than this one, which has a little bit less surface area than this one. So the larger surface area helps to explain the boiling point difference a little bit, but especially between these two, that specific factor is not much of a difference between them, right? These two have pretty much almost the same exact surface area. And surface area is relevant because of London forces, right? So whenever some structure and some other identical structure line up and attract, if the electrons are just randomly shifting to one side, then the neighboring structure of the electrons will randomly shift and create some temporary partial charges to attract. So that can happen more readily over the surface of the structure if there's more surface area to the structure. So that explains why this boiling point is relatively low. But a much more significant reason for that has to do with the hydrogen bonding. So when it comes to primary versus secondary versus tertiary amines, I want to keep in mind that the primary amine has more sites for hydrogen bonding than the secondary amine. And the tertiary amine can't hydrogen bond unless it's mixed with something, because it doesn't have any protons directly connected to the nitrogen, right? So here, the big electronegativity difference there, and this is significant but not massive, is going to create some pretty big partial positives and partial negatives. So this structure has lots of sites where it can attract to a neighboring structure, 3 really, and then a minimal but somewhat significant attraction there. And so those attractions will hold the molecules together. It'll take a higher temperature to separate them, right? Remember, boiling point doesn't break up the molecule. It only separates it from its neighbors by breaking the intermolecular attractions, in this case, hydrogen bonds, dipole-dipole, and London forces. Here, again, the nitrogen-carbon electronegativity difference is pretty minimal, but the nitrogen-hydrogen is fairly big. But I don't have as many large partial charge sites to form as many attractions. So here, maybe only a couple attractions with the neighbors, and if a couple of those break, it's free to evaporate, so it doesn't take as much energy or as high a temperature to boil that and separate it from its neighboring structures. Here, the boiling point's much lower because even though there is a dipole, it doesn't create very large partial charges. The nitrogen's lone pair can't really hydrogen bond with anything because all the hydrogens are bonded to carbon, and they only have very minimal partial charges. So here there's a minimal dipole-dipole between the structure and a neighboring identical structure and some London forces, but that's not much. Doesn't take much energy to break those attractions, so the boiling point's pretty low. This is just an informational slide. I always like these names. Putrescine, because it's putrid. Cadaverine, because it smells like a cadaver. So these amine compounds sometimes have really bad odors. And we're also familiar with pyridine, which the name of pyridine doesn't have anything to do with its odor, but it also smells really bad. So a lot of these volatile, meaning that they evaporate fairly readily, amines are smelling pretty bad, and so we try to avoid using them unless we need them for synthesis. All right, so we talked about amines acting as bases already. They're better bases than alcohols and ethers, right? So we think about alcohols and ethers. What's the difference between that versus an amine? Well, the difference is for an alcohol or an ether to act as a base, here we're talking about the traditional Bronsted-Lowry definition, it would have to pick up a proton from some acid. And why are alcohols and ethers not as good at picking up a proton? Well, because the resulting structure is going to have a positive on an oxygen. And since oxygen is much more electronegative than nitrogen, well, at least significantly more, the positive charge is going to start ripping these electrons back, and it's just going to go back. Right? So when we say it's not a strong base, what we mean is thermodynamically, if it were to act as a base and pick up a proton, the resulting conjugate acid is especially unstable, and so that equilibrium is going to favor the reactant site. In the case of a nitrogen, it's pretty good at stabilizing a positive charge, and we can see that with its moderate pKa. Right, the lower the pKa, the more unstable it is. So this is a pretty high, moderate to high pKa for a positively charged atom. When oxygen picks up a proton and becomes positive, the pKa of that is usually around 0 to 2 or so. It's pretty low. And so oxygen is not good at stabilizing a positive, especially compared to nitrogen. So the nitrogen's a pretty good base. It can readily pick up protons from anything that's even weakly acidic, because we know the equilibrium will favor the side with a higher pKa. And in this particular example, we have a 6 pKa unit difference. So if we were to react these together in water as the solvent, we would have 1,000,000 times more products compared to reactants because of how product favored that process is with the higher pKa. So this is a situation where we have two neutral reactants, which look stable because they don't have any formal charge, but they're actually favored to produce two charges. So the resonance helps us stabilize this. But nevertheless, we still have two full charges that look pretty unstable. So it's not always easy to judge which side is going to be favored, which is why the pKa values are so helpful, because they allow us to say whichever side has a pKa that's higher is going to be favored in equilibrium, and quantitatively how much it's going to be favored based on the difference between the two pKa units. So here are some other pKa values for some amines. So what are we noticing here? These are all really pretty similar. They're all real close to 10. Very similar to the one we just looked at. A pKa of 10 is a relatively high value. So these are instances where the nitrogen's pretty stable with a positive charge, specifically because it's not super electronegative. It won't rip the electrons away from the proton and force it back to where it started. It can actually share pretty effectively those electrons even though it's positively charged. And that's true for most of these. So let's see some different pKa values here for some other amines. What's the difference here? Well, these are significantly lower, which means these acids are stronger than the ones we saw on the last slide, which mostly just had standard R groups or hydrogens attached to them. So why is this nitrogen more stable with a positive than this one? Because this one had a pKa of around 10, as we just saw on the last slide. Well, we know pKa is a thermodynamic quantity. It tells us about the equilibrium. And so in these instances over here, when the nitrogen picks up a proton, since this pKa is higher, that equilibrium is going to be pretty product favored in general. If the pKa is lower, it means that it's not going to be as product favored. It might be a little bit more reactant favored. And so what is happening here? Well, the key to this, to understanding these three specifically, is resonance, right? So if this lone pair gets in a p orbital, which it would, and that p orbital overlaps with the p orbitals of the ring, there can be resonance there. It's a minor but significant resonance contributor, where the electrons can swing around and be positioned on these different ortho and carbons that are ortho or para to the nitrogen group. So that resonance adds a little extra stability to the neutral amine, and that shifts the equilibrium back toward that side, making the product a little bit less favored and a little bit less stable compared to the reactant. Right? So it's not like there's something about this structure that makes it a lot less stable than this structure, but pKa units aren't necessarily just an absolute measurement of how stable something is. They're comparing the stability of the product side versus the reactant side. And if the reactant side has a little extra resonance stabilization, that's going to cause the equilibrium to favor that side a little bit more, which by default means it's disfavoring the product side and lowering the pKa of that, meaning that when it reaches equilibrium, there's going to be less of it than there would normally be due to the stability on the other side. So we see pKa's around 5 for aniline and aniline derivatives. They're not quite as stable, not really inherently, but simply because the other side is stabilized by resonance, so they shift to the other side. Because pyridine has a conjugate acid with a similar pKa, students often think that that lone pair is in resonance, just like this lone pair, but that's not true. This lone pair is not in resonance. This lone pair cannot move into the ring. The ring is already, well, I should say that. This lone pair can't move into the ring specifically because it's not in a p orbital, right? This nitrogen's p orbital is already occupied with these pi electrons. So the, if the nitrogen's p orbital is already occupied, then the lone pair can't also be in it. The lone pair has to be in an sp2 orbital. But because the sp2 orbital is relatively compact and holds the electrons pretty close to the nucleus, it stabilizes them. So we have a similar situation here, but for a different reason. The pyridine's pKa is a little lower than we would normally expect for an amine, because most amines have their lone pair in an sp3 orbital. And that's more elongated. The electrons aren't that close to the nucleus, so they're more available to be shared with a proton. And when that forms, it won't be as likely to go back as it will be forward, and that's what gives me the higher pKa, the forward favored nature of the reaction that produces the conjugate acid. Here though, because the nitrogen's lone pair is in a more compact orbital, it's more stable, that causes the equilibrium shift back toward that side a little bit more, and that lowers the pKa of the resulting acid because the equilibrium in which it forms disfavors that side, which means it's not going to form as much of it when it reaches equilibrium, which means it has a lower pKa. This one here is very low, to the point where this is basically a strong acid. This nitrogen is not going to hold on to this proton, and that's because this lone pair is not just involved in resonance, it's needed to make this ring aromatic. Right? So we talked about aromatic compounds. We said we need an odd number of pi electron pairs in a fully conjugated ring. For something to be aromatic. These are the conditions or criteria. So as long as that lone pair is in a p orbital, I've got 1, 2, 3, an odd number of pi electron pairs in a closed, fully conjugated ring, because there's a p orbital on every one of these carbons overlapping side by side. This is an aromatic ring. If the lone pair gets shared with the proton, it's not aromatic anymore because now this nitrogen has no option but to be sp3. And so again, this product is not particularly unstable, nor is this one, nor is this one, but relative to its conjugate base, which is stabilized by being aromatic or just stabilized through some minor resonance, that is going to really favor the weak base side of this equilibrium, which means by default, the conjugate acid side of the equilibrium is not favored, and that's what produces a low pKa. So when the equilibrium shifts away from the acid, that's by definition what creates a low pKa for that acid. So you be asked to explain some of these pKa values based on those equilibrium analyses. In terms of solubility in water, typically your amine has to have 5 carbons or less to be pretty soluble in water. And so, typically if I have 4 carbon chain, or maybe I've got, a couple different carbons, 2 carbon chains or 1 4 carbon chain, these amines are going to be able to form attractions with water. Even if you have a tertiary amine, there's going to be enough partial negative here for that to form a nice hydrogen bond with a water molecule. And so the entropy associated with mixing and the extra variety associated with mixing is going to promote these small amines with relatively small R groups to dissolve pretty readily in water. But once you extend the carbon chain beyond 4 or 5 carbons, you start to get into a situation where even though this part of the structure can hydrogen bond with water and will readily mix with water, if the rest of the structure is much larger in size and low in polarity, the water molecules are not going to effectively attract to it compared to how they could attract to one another, so they would push that out into a separate layer or potentially cause it to form into a micelle or something like that. So you want to be aware that the solubility, as with most compounds, shouldn't be a big surprise. The larger the low polarity group attached to the molecule, the less polar it's going to be in water. However, you can increase the polarity of this dramatically by treating it with an acid. So if I react this with any kind of acid in water, the acid will probably produce H3O plus, and then the amine would pick off a proton from the H3O plus, and that would convert the amine into an ammonium salt. So now, even with this large R group that water can't really effectively attract to, by having the amine pick up a proton, I've dramatically increased the strength of its attraction with water molecule. Right here, the large partial negative and large partial positive can form some nice hydrogen bonds with water. And I can form a couple there, I can form a couple here. Large partial negative, partial positive attraction. So those hydrogen bonds are pretty strong, and that helps to dissolve it, but not strong enough when the water molecules would also have to surround this other part of the structure, and they'd rather just get rid of that and attract to one another where they can all just form lots of nice hydrogen bonds together. But once the nitrogen picks up a proton and becomes charged, now you have ion dipole attraction, which is even stronger. So the ion dipole attraction here, being especially strong, allows the solubility of the structure to be much, much larger. So that means that, let's say you've done a reaction in which you formed an amine. So you have a reaction mixture that includes an amine, and maybe it's bonded to some big low polarity group, like an aromatic ring maybe, and maybe there's like another ethyl group here or something. And maybe you've got some other impurity. So maybe you did a reaction where you started with this molecule, a nitro group, and you convert it into an amine. If your reaction mixture still has unreacted nitro ethyl benzene, in addition to the product, which is the 4-ethylaniline, and these are both relatively low in polarity, it's difficult to separate them. You might need to use column chromatography or something to separate these. But what can actually work here quite nicely is a liquid-liquid extraction in a separatory funnel. So I might ask you a question about this. So what you would do here, how this would work, is you'd have an aqueous layer in your separatory funnel. You'd probably have a terp-butyl methyl ether layer, like we often use. Since these are both relatively low in polarity, we'll call this A and we'll call this B, they would both probably start off in the low polarity solvent. So what you would do then is to add an acid, a strong acid like HCl or sulfuric acid or something like that, and the strong acid would produce H3O plus in the aqueous layer. And the pK of that is around 0. It's pretty acidic compared to the conjugate acid that would be formed when this nitrogen picks up a proton. So that equilibrium would favor the nitrogen picking up the proton, and that would convert this group into a charged structure. Once it's charged, we'll call this A plus, since it's the structure with an extra, we'll call it HA plus, since it picked up a proton and became positive. Once it's positively charged, now it can form ion dipole attractions with water molecules. That's a lot stronger, potentially strong enough for the water molecules to surround the whole structure and bring the whole thing down into the aqueous layer. So what would happen then, after you shake that up, is in your separatory funnel, then you would have compound A being protonated and compound B not, because it doesn't have a basic site. It's not an amine. It's a nitro group. Nitro group's not very basic. So then you just drain out the bottom layer, which would have this dissolved in water. And then if you just add OH minus or some base that's strong enough to pick that proton back up, you convert a HA plus back into A, and that would precipitate or form a separate layer. At that point, you could collect it, and you've effectively separated it from B. So doing an extraction under acidic conditions will usually convert an amine into an ammonium salt, which would then make it soluble in the aqueous layer and allow it to be separated from any other low polarity substance that would stay in the nonpolar layer. We talked about that one. Oh, okay, so we talked about this one, and we explained roughly why the equilibrium might not favor the positive charge as much relative to the neutral structure because of the resonance stabilization of the lone pair here that we don't have over here at all, because there's obviously no lone pair. But we want to talk a little bit more detail about some differences in aniline derivatives depending on substituents that might be attached to the ring. So as we said, most alkyl amines have pKs around 10. Most aniline derivatives have pKa's around 5 or so, but there is some variation there, especially here, that we want to explain. And so the idea here is, if there's some group connected to the ring, it could affect the nitrogen's ability to pick up a proton. Right? So if I have a group that can donate electrons into the ring through resonance, like an OH or a methoxy, then to some extent, that's going to put some partial negative on this carbon. It'll also, as the electrons swing in, these might move out here, so I'll push some partial negative there. These could continue to swing around and push these here. So we'll get some partial negative here. So if I have a group that can donate electrons through resonance into the ring, it should create some partial negative on carbons that are ortho and para to it. So if you have an amine group on one of those ortho or para carbons, that partial negative, which will also exist on the conjugate acid, that negative being right next to a positive forms an attraction, helps to stabilize it. So this positive charge is slightly stabilized, which means the equilibrium helps to shift toward that side versus the other side. So likewise, if you have a group that withdraws electrons, you see the opposite. So the CN has a CN triple bond, and through resonance, the electrons can shift over here, and that pulls electrons out of the ring and makes this carbon positive. And when electrons shift over, then this carbon's positive, and so is this one. So putting a positive there means that you've only made this nitrogen more positive, right? The negative helps to shift electrons toward that positive to balance it and stabilize it. The positive pulls electrons away from something that's already positive. It's only going to make this nitrogen more positive. The repulsion between those positives makes it unstable. So if it's unstable, it's going to be shifting back in the equilibrium, which means its pKa is now lowered, because relative to its conjugate base, not that many molecules are going to remain in the acidic form. So you also want to be aware of how resonance effects across of an aromatic ring can affect the stability of a charge and the pKa that results from that. We talked about that difference and how the aromaticity of the ring is affected by the nitrogen being protonated. So just to recall that, we said for this structure specifically, because it is aromatic only when the nitrogen has a lone pair, if I protonate that versus deprotonating it, the equilibrium is going to greatly favor the side where the ring is aromatic versus the side where it doesn't have the aromatic stability. And so that's why the pKa of the pyrrole, the protonated pyrrole, is so low, because in equilibrium with the unprotonated aromatic stabilized pyrrole, the equilibrium is going to favor the aromatic side. Over here we said it was because of the sp2 orbital that those are electrons in. Those electrons are in. The sp2 orbital is relatively compact, so the nitrogen nucleus pulls that in and stabilizes it pretty well, and that means it's going to be pulled away from the hydrogen, so a lot of the molecules would exist without that proton. So pyridine is a relatively weak base. It's basic enough to pick up a proton and stabilize it fairly well because its pKa is high enough, indicating that that's relatively stable, but a lot of times it will shift back because of the lone pair being in an sp2 orbital, being compact and being pretty well stabilized by the nitrogen when the proton's not there. Let's see, probably going to skip this section here. I usually don't ask questions about the Henderson-Hasselbalch formula. The main point of this is to just point out something that, for me, when I was an undergraduate and we would talk about biochemistry or biology, a lot of times amines are represented in biology or in biochemistry with positive charges. And so in water, if you have an amine, in pure water, amines generally, for the most part, favor the neutral form because of the formal positive here. You know, if that's just reacting with water, and water loses a proton to produce OH minus, the pKa of water is around 15. The pKa of the conjugate acid of the amine is usually around 10, and so that's why the equilibrium favors the reactant side. So, you know, when I saw this in chemistry courses, and I was like, well, amines are more stable in the neutral form than in the positive form, and this equilibrium demonstrates that, because equilibrium favors the side where it's neutral. But in biology, it's not just reacting with water. When you're inside an organism, you're at the pH of that organism. And in an organism, and depending on the type of tissue, you're usually at a physiological pH. Most fluid and tissue in organisms has a pH of around 7.4. So if we plug that in here to the Henderson-Hasselbalch formula, and we plug in the pKa of a typical conjugate acid of an amine, which is around 10 here, we can actually solve for the ratio of how much of it is going to be in the conjugate base form, which is the amine form, versus how much of it is going to be in its conjugate acid form, which is once it gets protonated. So if you plug that into your calculator real quick and just solve for this ratio, you'd have to subtract 10 from both sides. So you'd have a negative 2.6 over here, giving you the log of that ratio here. And so then to get rid of the log, you'd have to take 10 to the power on both sides. So if you do 10 to the negative 2.6 power, you get that this ratio is equal to 0.0025. So for every one molecule that's in this form, you have 0.0025 molecules in this form. Or if we were to flip that ratio and just take the reciprocal of it, we would find that about 400, so there's about 400 of these for every one of these. So now we see the opposite of what we see in distilled water. The majority of the molecules exist in the charged form rather than the neutral form. So that's why in biochemistry textbooks you'll see amines typically existing, already being protonated, because at the physiological pH, most of the molecules exist in that form versus not being protonated. And that Henderson-Hasselbalch formula helps us demonstrate that. All right, so now we can talk about how to make amines. And so we've talked about how to do that already this semester. So first we want to start by reviewing some of the reactions we already saw. So here's one. One way to make an amine, and this extends the carbon skeleton by 1 carbon, is to start with an alkyl halide. This one could be primary or secondary because the CN- is a great nucleophile. Even if it were a secondary carbon, it wouldn't be too crowded for the CN- to come in here and push out the leaving group. And that's what installs the extra carbon, right? So we had 1, 2, 3, 4, 5 carbons here. Now we have 6. And then we saw in chapter 21 how we can use lithium aluminum hydride to reduce a cyano group or a nitrile into an amine. Right? So that works pretty straightforwardly as the hydride is delivered to the carbon, pushes electrons to the nitrogen. And the hydride is so unstable with a negative, it would deliver another one. Another hydride would come in here, push another pair to the nitrogen, which would give me this structure. The -2, and then that would accumulate in solution until water is added. Obviously the nitrogen would pick up a couple protons from a couple different water molecules to produce the amine. So that's one way we talked about previously to make amines. And that helps us with the second quiz question for today. We've got a secondary leaving group, or leaving group on a secondary carbon. Notice the dashed wedge here means the bromine's pointing away from you if you're in front of the screen. So we expect this good strong nucleophile to come in from the back side and push the bromine out. If we were to imagine this as a chair, and we had the bromine with the dashed wedge, that means it would be pointing down, so we could imagine it like pointing down here. And the methyl group has a solid wedge, so it's pointing up. the Cn minus would have to come in here to push the bromine out from the backside, right? So it's not going to replace the bromine on the same position spatially where the bromine left. It has to come in from the backside and replace it with the opposite configuration. And that means it's going to end up where both the methyl group and the nitrile group are both having solid wedges, right? So if the bromine's pointing away from you, the Cn group has to approach from the front to push that out the backside. And so the product that you would draw there initially, just after step 1, would have the Cn group with a solid wedge. Then the lithium aluminum hydride is going to deliver 2 hydrides to the carbon. It's still got a solid wedge though, because we're not affecting anything on this carbon. We're not doing anything with this proton or this carbon other than putting a couple more hydrides on that carbon and shifting the electron pairs onto the nitrogen. And then the water would be provided to protonate that. So the final product you'd want to draw there would have both as solid wedges and an NH2. So we started with 7 total carbons, and now we have 8. So you want to pay close attention to the stereochemistry when the cyano group attacks. It should do so from the backside. Another way to make an amine, which we also saw in chapter 21, is to take a carboxylic acid and convert that into an acid chloride with thionyl chloride. So after step 1 here, you would convert the carboxylic acid into an acid chloride. And then you could add ammonia. So if I wanted there to be R groups here, I could do that as well. Right? I could use up to a tertiary amine here. I could put as many R groups as I want, or hydrogens there. So here I'm just showing a secondary amine. That's going to come in. It's going to push electrons up to the oxygen. When they swing back down, it's going to push out the chlorine. So that's going to temporarily give me this. I misspoke. I made a mistake. I do need at least 1 proton here. So in this reaction scheme, I could use ammonia, which is what we have here in the form of NH3, or I could use a primary or secondary amine. I can't use a tertiary amine, and going through the mechanism really helped me realize that, because I didn't think about it initially off the top of my head. When the nitrogen comes in here, push electrons up, they swing back down, push out the chlorine. If there's no proton attached, if this had 3 R groups, because I started with a tertiary amine, there'd be no way to stabilize its charge. And we need to pick a proton off here to provide the lone pair to really make this stable, because the lone pair engaging in resonance is really going to stabilize that effectively. So another molecule of the amine is usually what ends up deprotonating there. And that would produce that product. So I could have 2 hydrogens, 1 hydrogen in an R group, or 2 R groups if I'm going to make this amide. So we talked about making amides in chapter 21, and then we did also say an amide is also reactive and can be converted into an amine with LEH. So LEH is pretty versatile. The hydride can be delivered here, push electrons up, and that gives the structure here. And then we said once the oxygen forms a negative charge there, it will form a nice ion dipole type attraction to the aluminum, and that really helps stabilize that charge. So then the nitrogen's lone pair can shift in and push that out. And then that is susceptible to another molecule of LAH attacking the carbon and pushing electrons here, which is what produces the product. And so I might expect you to go through any of the steps involved in this process or the one on the previous slide and draw the full mechanism for any of those steps for those two methods of producing an amine. The third way to produce amine that we already discussed this semester is from a nitro group. So there's really two ways to do that. The hydrogenation is not very commonly done because you need a very high pressure and often a very high temperature. And when you do that, sometimes you might start hydrogenating the aromatic ring. Or if there's other alkenes, those would definitely be hydrogenated by the metal catalyzing that reaction. If there's a ketone, that would also potentially be hydrogenated. So lots of different pi bonds can be hydrogenated. And so only if I have a simple structure that doesn't have any susceptible pi bonds would I potentially do that to convert a nitro group into an amine. So the reduction with a metal is more versatile because it's a little bit more of a mild condition and it doesn't create the likelihood of other groups reacting as often as hydrogenation would. But we do know that the metal, these different metals with acid can also reduce a CO double bond. So that also would be a functional group that would interfere with the reduction of the nitro group. So if I use an EAS reaction, I can put a nitro group onto an aromatic ring, right? These two will react together to produce a nitronium ion. We talked about that in chapter 19. And then the ring would attack that. And then once the ring is re-aromatized, you'd have the nitro group there. And then often zinc and HCl are used to reduce that down to an amine. And so that's especially often used if you're starting with an aromatic, a nitro group on an aromatic ring. And we'll see why that is and what we can do with this moving forward next week. So if you want to make an aniline or aniline derivative, starting with a nitro, reducing it to the amine, and then you could add other R groups or something onto there, depending on what your final structure is that you're trying to make. In this reaction, you do need NaOH, and that is because the acidic conditions, if I have a significant amount of H3O+, then nitrogen is going to use its lone pair to pick up a proton from the H3O+. And so if I don't add the NaOH, I'll end up getting this, an ammonium salt. So if I specifically want aniline, I need OH minus to pick one of those protons back up. So I need the acidic conditions to convert the nitro group into an amine. To do the reduction, if I'm using this bottom method here, in step 1, I would add the metal and the H2O plus together. But since I'm adding acid, it's going to protonate the resulting amine group. So the OH minus is just there to deprotonate that and get back to an amine instead of an ammonium salt. All right, so here's a new way to make an amine. And this method is got some of its own problems. And we'll see some better methods as well. So since we said amines can act as bases or nucleophiles, which is basically the same as a base because it's a Lewis base, as a nucleophile, it can attack a carbon group. So, this is going to be limited potentially by sterics, but if there's a good leaving group there, the nitrogen's a pretty decent nucleophile, it can attack, push out the leaving group. So this would be usually an SN2, and it would require it to be primary or secondary typically. The methyl group's not very sterically hindering at all, so that can easily come in there and push that out and make this product. And then I would use two equivalents of this, because once one attacks to form the ammonium salt, the second one would be around to act as a base and depronate to give you this product. So I can go from ammonia to an amine. The problem is that this, once it forms, is also nucleophilic. So as this starts, if this is the product, if I want to make this and just stop with methylamine, and I don't want to keep reacting, it's difficult to stop it from reacting further, because this is now nucleophilic again. And before all the ammonia has a chance to react, some of this product will start forming as a fraction, maybe I'm 10% of the way through, 10% of this ammonia has formed into product. I'm starting to build up a significant amount of this product. It's going to be the one once in a while that starts colliding here, pushing that out. And so it's going to start getting another methyl group on it. And then maybe an initial amine will pick off this proton, or maybe another one of the product, either way. So now I start getting too many methyl groups attached. And even now, it's still nucleophilic, so it could pick up another methyl group. And eventually, it's going to have methyl groups on all four sites. So what we're saying here is, this reaction will not stop at a primary amine. It won't stop at a secondary amine. It won't stop at a tertiary amine. It will go all the way to the quaternary ammonium salt, which is this structure here. If that's what you want, great. But if you want to make a primary, secondary, or tertiary amine, this is not a great method, because it's really impossible to prevent all the extra R groups from connecting there, because every time you make another R group connect and re-up that lone pair, it's ready to pick up another R group and continue to be alkylated. So we need some alternatives. So the first couple alternatives we're going to see today, and the rest we're going to see next week, along with some reactions that amines undergo. But the first couple alternatives here are specifically for making primary amines, because this method here, we can put a bunch of R groups on, but we can't stop at a primary amine. So what if I want to make a primary amine? Well, I can start with the same type of thing, some kind of alkyl group on a leaving group. So this would be like a chloride or a bromide or something. And instead of adding ammonia, I'm going to add this N3. So the sodium has a positive, N3 has a minus. So what does N3 look like? Well, it looks like this. Oops, there's no lone pair there. Sorry about that. So this has a positive, negative, negative. So this ion is stabilized through resonance, but it is overall negative, because there's two negatives and one positive. It's a pretty good nucleophile. It would have a sodium to balance its charge, but once I put it in solution, the sodium would be a spectator and go away. It would be solvated and separated. So this would attack here, push out the leaving group, and then you'd have it connected there. And then you just need to reduce that down to the amine. Right? So what this structure here would look like would be this. So with the hydrogen, basically you're just adding a molecule of hydrogen across this double bond. So you add a hydrogen to each nitrogen, and then you do it again, and that breaks that up, and you end up with two nitrogens there. So here's the mechanism with the LAH though, right? So we showed this. If I have a leaving group here, like a chloride or a bromide, I can get this nucleophile to attack once and push that out. Once that's formed, in a second step, so this would be really 1 to produce this substance, and then this would really be 2 and 3. So in the second step, the lithium aluminum hydride is added. That's going to attack here and push these electrons over there, which is going to give me this structure here. Right? This hydride came from the LAH. Then this molecule will undergo an intramolecular step where these electrons swing in to make N3, N2 with a triple bond, I should say. And this nitrogen leaves and creates a negative. And so in step 3, when the water, this would accumulate, and then later when the water's added, it would pick up a proton to form your primary amine. And what makes this reaction work so well is the production of N2. It's extremely stable. We know nitrogen gas is a great inert atmosphere to work with during reactions. It's not reactive. It's quite stable. And that triple bond that forms between those nitrogens is an especially stable bond. It's not technically leaving in this case. The N2 is not technically acting as a leaving group, because the leaving group would have to take the electrons with it. It's really this pair of electrons swings in and pushes out this. This is the leaving group. But the nitrogen molecule is really very stable. This negative charge on nitrogen is not very stable. The only reason it gets pushed out is because the nitrogen is so stable, and since it's a gas, it leaves the reaction I wouldn't exactly call it a leaving group, and even there the word leaving is misspelled, so ignore that. Since this electron pair swinging in forms a triple bond, and that's a gas, it bubbles out of the reaction. It can't come back in and do the reverse. So the reverse of this process is pretty much insignificant. And that's what helps to drive it forward toward the negative. And that's why this accumulates, even though it's pretty unstable, until a proton source is added where it would pick up a proton and produce the amine. So that's a nice way to convert overall an alkyl halide into a primary amine without changing the number of carbons, right? 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6. So basically we're just having this N3 come in as a nucleophile and then reducing the N3 to an NH2. The other method to produce a primary amine specifically is the Gabriel synthesis. And the Gabriel synthesis involves phthalimide, which is a structure here. So this is very cheap, easy to get. Oops, didn't mean to do that. KOH can be used to act as a base and pick off a proton from the phthalimide. I think you can probably also just buy potassium phthalimide and skip this step. Normally a negative on a nitrogen is really pretty unstable, but in this case there'd be resonance there, and the resonance would spread the negative charge out over both oxygens and the nitrogen, so that's really quite stable. That resonance really helps to stabilize it, but still nucleophilic because we still have a negative here, and so it could still attack. And so the idea here is we're going to do an SN2, and so we would have our R group, which might be methyl or an ethyl or propyl or whatever, and then we have a leaving group like a bromide or something like that. So that's what this is representing. So that would come in there from the back side and push that out. And right here I'm just happening to use a propyl group, just as a specific example, but pretty much any R group that's not tertiary, because tertiary would be too crowded for it to come in. Primary works best, but it could also be a secondary carbon. So that nitrogen is going to attack there, and that's going to give me this structure. Right? So my propyl group would be connected, or whatever group would be connected to that nitrogen. So then the next step would be performed in one of two ways. Either you're going to use a strong acid concentrated with heat to hydrolyze these amide linkages through the mechanism we saw in chapter 21, which breaks up the amide and forms carboxylic acids and your product amine that you're interested in trying to make. Or you can use hydrazine as a reactant, and the hydrazine will come in here, push electrons up. eventually this will be pushed out as a leaving group, and then the two nitrogens will bond to those two carbonyls because the six-membered ring is a little bit more stable than the five. Either way, you get the primary amine expelled from that group, from the phthalimide functional group. So you don't have to worry about the mechanism for this part, but you should know that this is one way to make a primary amine along with the azide synthesis going through the azide intermediate as well. Those are probably two good ways to make primary amines. So there's plenty for you to practice there in preparation for exams next week. Next week's exams are going to cover day 25 and day 26. And so practice up with those specific examples. Let me know if you need any help or have any questions about any of that. And then our last lecture of the semester, as I said, is going to be next Wednesday instead of Monday. We'll review on Monday, so you're welcome to come to the live stream here on Monday to ask me any questions you may have about next week's exams, and I'll come with some examples to look at and explain as well. But the final lecture is going to talk about mainly reductive amination, which is an alternative for making amines that's really quite effective. And then a couple reactions that amines undergo, including formation of a diazonium salt. There's a lot of synthetic utility to that. So we'll cover the last few sections of chapter 23 next Wednesday. I don't want this here.